All right, so in this Memorial Day screencast, I'm going to explain how to do more complex redox balancing. Keep in mind that we only barely touched on how to balance redox reactions before we had to do the test on Friday. So we're going to go back on Monday and continue to work on some of the more basic redox reaction balancing questions, and then we'll also practice some of these as well. But don't freak out if you're somebody who doesn't have any clue how we're doing this. You'll have a chance to practice it on Tuesday because we don't have class on Monday. All right, so here's the reaction. I have an iron ion. Now keep in mind there's a geez, what do they call spectator ion that's involved here. And in fact, I want you to imagine this is the spectator ion is just like the spectator ion we dealt with on Thursday. So it would be the sulfate ion. And then we have the permanganate ion, the MnO4. And if you recall from that lab, potassium was the spectator ion with that dude. And then we have the formation of the Fe3 plus and the Mn2 plus ions. Now, the spectator ions associated with those two are not really important, and you may recall that I didn't even include them in the lab write-up itself. But, well, you could probably figure out what they are, but I'll ignore that for now. If you don't, then don't sweat it. So let's figure out how we go about balancing a redox reaction like this one. And I'll take you through the process. Let's go step A. We're going to go ahead and pull out the Fe2 plus, and that becomes Fe3 plus, right? And you can see here that we have a +2 oxidation number and a +3 oxidation number because it'll match up the ion itself. And if this is the case, I need to make sure I add one electron. Now, slow down if you don't know why I needed to add an electron to balance this out, and take a look at it carefully. And then for the second half reaction, I'm going to take the manganese, and it's MnO4 minus. And if you do the calculations properly, you'll find out that the manganese has an oxidation number of +7. And this is going to lead to a manganese +2 ion, so that means this will be a +2 as an oxidation number here. And of course, if that's the case, then I'm going to need to add electrons to one side. Can you predict what side I'm going to add it to? I hope you can. I'm just going to scooch this thing over here because I need to add my 5 electrons over on this side in order to make sure that we have the same charge on both sides of the equation. Now, of course, we can see we got a problem here because in the equation at the top here, we only have 1 electron involved. And in the equation on the bottom here, we have 5 electrons involved. So pretty easy fix. We just multiply this top by 2. And when we do that, I'm just going to keep the color as blue so we can see that there's a difference here. We have 5 Fe's, and this is our +2 ion here. And this becomes 5 Fe, and that would be the +3 ions, plus 5 electrons instead of the original 1 electron. And then you can see how we can combine this one and this one together. And when we do that, we have, let's go green to make this all a completely different thing. We're going to have 5 Fe's plus, oh, it's Fe, which one is that? Fe2 pluses, okay. 5 Fe2 plus, you can see that I brought it over from right there. And then I'm going to bring in my permanganate ion and go ahead and toss in the 5 electrons associated with the B equation. And then we're going to go ahead and put in the arrow to the Mn +2, which you can see is right there. And I'm going to add this tail end of this equation, this half reaction. So the plus the 5, whoa, undo, 5 Fe3 pluses, and the 5 electrons. I'm going to put the AQs here so we don't lose that. This is certainly all of them are going to be AQs. Squeeze AQ into here. Okay. And when you look at this reaction, is it balanced? Well, of course, I'll go ahead and erase our electrons since they balance up. Is that all balanced up? We have, let's see, we have 5 irons. We have 1 manganese on each side. Uh-oh. But what about the oxygen? So something's wrong here because this is not a balanced equation since we don't have oxygen on both sides. And you might say to yourself, well, that's impossible because if you have no oxygen on the product side, how could you possibly balance this? Well, if you recall, going back into that lab, I asked you to look carefully at the reaction that was on the first page. And if you can, I want you to pause the video right now and go take a look at that lab handout. That's the lab called L-quantitative redox. So you can look in Notability or in Dropbox for this thing and look at that equation and then tell me what's different about that equation from what I've written here, and then come on back and we'll talk about it. All right, so go ahead and hit pause. 3, 2, 1, now. All right, you cheaters, you maybe didn't pause and you kept going. But what many of you saw is that included in the reaction that you saw, the lab handout, was in the reactant side, you had 8 protons, 8 H pluses, and on the product side, you had 4 waters. And in fact, that's exactly what we have to do. We have to actually make sure that this reaction here, this reaction that we have in green, has to take place in an aqueous solution, an acidic aqueous solution. And if you have an aqueous solution that's made up of primarily of an acid, so if it has, say, sulfuric acid like we had in the lab, then it's going to have a bunch of protons floating around its solution, and it's going to have water, because of course, if it's in an aqueous solution, the solvent is water. So if that's the case, let's go ahead and take a look at what we can do with this reaction here. So let me circle up this reaction and center it a little bit more here. And I'm actually going to blow it up slightly. Okay. And I want you to imagine if you could add water. So if you could add water to this whole system, you would want to add it to this side. Why do you say that? Well, because we have oxygen on this side in our MnO4, and water carries an oxygen with it, and so if we're going to try to balance things out, then we have to make sure we bring the water into here. Well, you can see here that we need to have 4 waters here, because I have 4 oxygens, and if I put a 4, and I'm going to do this in red just so we can see the difference here, in front of our water molecule, and we shouldn't forget that this is a liquid, then we can see here that 4 times the assumed 1 associated subscript there of the oxygen would mean you'd have 4 oxygens on the product side to go with the 4 oxygens on the reactant side. Beautiful, right? However, the problem we have now is that notice that I've just increased this reaction by putting in hydrogens on my product side. And I don't have any hydrogens here. So why not just add them in? In fact, I can just do that. So now I'm going to add hydrogens, but I'm going to do that in the form of protons. In other words, acid is going to be included in this reaction. And how many protons would be required? Well, it would be 4 times the 2 that you see here. So 4 times 2, or 8. So that means I'd have to run over here and put an 8 in front of my hydrogen. Now, as long as this was done in an acidic environment, in an acidic aqueous solution, which of course, as you recall from the lab on Thursday, it definitely was, then you can balance this thing out perfectly as long as you have the ability, which you do in this case, to add water, and then on the opposite side, add the H plus ions. So let's take a look at another reaction where we might need to add the water and the hydrogens, and that would be, we're going to use permanganate again because it's really handy to use permanganate. All right, so let me take a moment to write down the reaction. Hey, what's going on here? And I'll be back in a sec. All right, so here's my next reaction here. Now, the only thing that might be odd to you is to see is that this chlorine should be chlorine gas, right? Well, I'm going to say that it's actually dissolved in the liquid in which this is taking place, so in water. So everything is taking place in an aqueous solution. And let's go ahead and take a look at this, and I'll walk through it without even saying anything and see if you can figure out what's going on. All right, so that's my first half reaction. It looks a lot like the previous one. Here's my second half reaction. Now, the first thing we need to do with this is balance the particles. So I have to go ahead and chuck a 2 in front of that. Now, if I have to put a 2 in front of that, now I'm going to have a slightly different situation. I'm going to shift this whole thing, scooch it closer, and then I'm going to add not 1 electron, but I'm going to add 2 electrons to make sure I balance out the fact that I have the 2 chloride ions, so a total charge of a -2 over here. All right, so now what do we have to do? Trickier, huh? So you're going to have to multiply both reactions by something. So in this case, I'm going to multiply this reaction by 2, this reaction by 5 to make sure we're going to have the exact same number of electrons involved. So I'm going to hit pause and I'm going to write out what happens when we do this multiplication. I just realized it's being very naughty and not including the oxygen, so I should go ahead and back up and include the oxygen in my permanganate. All right, so there's my half reaction A, multiplied everything through by 2, and here's my half reaction B. All right, you can see how my reaction B now has the 10 electrons to go with my reaction A, which also has the 10 electrons. So we can go ahead and push these two things together. Shoot, I gotta shift things over here and continue to write. Okay, let's see, I have it all there. Yep. All right, so I can go ahead and get rid of my 10 electrons here. Boom, boom. And again, we're not done because we have oxygen on one side and we don't have oxygen on the other. So I'm going to go ahead and add in, once again, our water over on this side. Now, it's trickier here because now I have 8 oxygens over here. So that means I have to make sure I add in 8 waters altogether. So I'll have 8 oxygens on this product side. And now I have 16 H's. So over here, I might as well just put it over here. I'm going to add 16 H plus ions in order to balance this all out. There you go. Boom. See you tomorrow.